Good afternoon, everyone. I would like to present my poster. Good afternoon, everyone. I would like to present you to my poster. The topic of my presentation is carbon nano-onions modified with organoboron acid as a direct amide condensation catalyst. The formation of an amide bond is an important issue in synthetic chemistry as it has structured part of commonly synthesized chemical compounds. Amide synthesis is most often accomplished by direct condensation between amines and carboxylic acids. However, this reaction does not occur spontaneously under normal conditions and requires heating to high temperature in which a water molecule is released maybe above 200 Celsius degree. Standard and effective methods of amide bond formation involve use of coupling compounds such as dicyclohalocarboxylamide or carbonyl diimidazoles. Unfortunately, those reagents are usually expensive, used in stoichiometric amounts, and generate additional post-reaction waste. The solution of the problem is the search of methods of catalytic amidation. One of the well-known catalysts for the amidation reaction are aromatic boronic acids. Unfortunately, they are quite expensive. The problem of the catalytic method with the participation of boronic acids is the long reaction time, significant consumption of the solvent, and the lack of possibility of regeneration of the catalyst. Here a carbon catalyst containing carbon nano-onions and aryloboronic acid were present that are non-covalently attached to carbon nanostructure. The carbon catalyst consists of the phenylboronic acid, which is the direct fragment response for the catalysis of the reaction, the aliphatic chain for the distance that making the distance between the pyrene molecule and the phenylboronic acid, and also pyrene, which is the compound that can strictly bonded to the carbon structure that consists of sp2 hybridization. And at last, carbon nano-onions as a catalyst support and are absorbers of microwave radiation. Nano-onions can quickly absorb the microwave radiation. Aryloboronic acid was obtained by a four-steps linear synthesis. The substrate was an aromatic polycyclic pyrene compound. In the first step, it was brominated with N-bromosuccinimide in anhydrous dimethyl formamide. We used laurel peroxide as an active catalyst, which proved to be ineffective. In the next step, a bromide atom was substituted with an excess of nucleophilic. In next type, we substitute the bromide atom with lithium atom with using a lithium bromide. The reaction proceeds in a THF condition, so medium in a very low temperature. In the next step, a bromide atom of 1,4,5 dimeroalkane was substituted by nucleophilic addition of the lithium pyrrolate. After crystallization from after standard extraction and crystallization, compound 4 was obtained in 87 yield. In the last step, one of the synthesis, the bromide atom of compound 4 was exchanged for lithium by reaction with lithium bromide, and the obtained lithium derivative was reacted with an excess of trimethyl borate. After completion of the reaction by addition of an acidic ammonium chloride solution, and after the acidic base extraction, A crude reaction mixture was obtained, which was crystallized from methyl acetate. The aryl boronic acid 5 was obtained in 83% yield. The structure of direct compounds obtained was confirmed by analysis of 1H NMR spectra and 30C NMR spectra, and also with a spectrometric mass analysis. The overall yield of the synthesized was 47. The carbon catalyzed was obtained as a result of physical adsorption of aryl boronic acid on carbon nano-onions. The pp interaction between the carbon materials and the pyrene group allow for quite strong binding of the compounds. Effective confirmed adsorption was uniform confirmed adsorption was obtained by sonication, a suspension of carbon nano-onions, in a saturated toluene chloroform solution of aryl boronic acid. After centrifugation, washing with a fresh portion of the solvent and drying, a ready material was obtained for further research. Based on the weight gain of the carbon material used to prepare the catalyst, the amount of adsorbed aryl boronic acid on the carbon and nano-onions was calculated to be 1.2 milligrams per milligrams of carbon nano-onions. When the obtained carbon material is placed in a hot toluene, the aryl boronic acid desorbs and goes to the liquid media. After the cooling this solution, organoboron acid quickly goes onto the carbon nano-onions surface. The catalytic ability of the boronic acid, which was adsorbed on the surface, was investigated on a model example of amidation reaction between benzoic acid and anilines. Due to the advantages of the microwave method, uniform heating in the entry volume of the reaction mixture, direct energy transfer to the reactants, shortened reaction times, all reactions were carried out under microwave accelerated conditions. We only thermally catalyzed reaction. We not see any quite good yield when the components were combined together and heated only thermally at over 150 degrees. Heating the reaction mixture in the temperature range from 120 to 200 Celsius and for a time not longer than 120 minutes does not allow the achievement of the efficiency higher than 20%. Amide formation in the environment of toluene and in the presence of molecular sieves did not lead to the production of amide. We have determined that the amidation reaction is catalyzed by aryl boronic acid, preferably under solvent-free condition at 150 Celsius degree and during the 1/2 hour. The use of the carbon catalyst allows to achieve slightly higher yields as for the aryl boronic acid itself and a shorter synthesis time. Finally, the co-catalytic effect. We investigate the co-catalytic effect of additional dimethyl amino pyridinium oxide, which is an electrophile. And when this compound is combined together with the catalyst and aniline and carboxylic acid, after the heating of mixture, the yield of amidation compound was the highest. Next, we check the efficiency of the reaction between the various amines and carboxylic acid under the condition established in the model example. The obtained yields of the isolated amines range from 52 to 92%. The catalytic reaction was generally better from benzylamine than for aniline, especially because benzyl is a much stronger base than aniline. The amide was the last efficiency formed between the benzoic acid and the aniline derivatives, which has electron withdrawing groups attached to the aromatic rings. For example, nitro, halogen, and better for electron-rich aniline derivatives having electron-donating group, especially methox group. The postulated mechanism is based on the reaction of erythronic acid with a carboxylic acid, leading to the formation of mixture anhydrous. The reaction proceeds with releasing of water, and only when something which can catch water, or in a condition when water can remove from the reaction mixture, a reaction can proceed. Mixed anhydride can react in another step with electrophile, which we add to the reaction, dimethylamino-pyridinium oxide, exchange the boronic moiety, and form active ester, which can in the next step react with amine and form the amide. In a summary, erythronic acid was obtained as a result of 4-step synthesis with a total yield of 47%. Erythronic acid has been efficiently adsorbed on carbon nano-onions. A series of direct catalysis amidation reactions were investigated in a yield in the range of 47–92%, and using carbon nano-onions allowed to achieve catalyzed recovery and shorten the duration of the times due to the possibility to absorb microwave radiation. At the last, I want to thank you for the Marta Pawelska and grant number, which we can see on the picture. Thank you very much for your attention.